Decision trees operate by recursively partitioning data based on feature values. Starting at the root node, the algorithm selects the most informative feature to split the data. Each split creates branches based on feature values, dividing the data into subsets. This process continues at each new node until reaching leaf nodes that provide the final predictions. Each leaf node represents a final prediction class or value, depending on whether the tree is used for classification or regression. Let's visualize this process with a simple example showing how a decision tree classifies data points. In this example, we have two features, x and y, and two classes of data points shown as circles and squares. The decision tree looks at our data and decides to make its first split on feature x with a threshold of 5. For the left region, the tree makes a second split on feature y with a threshold of 5. After splitting, we have three regions. The upper left contains mostly circles, the right region contains mostly squares, and the lower left has mixed data. Here's the final decision tree that corresponds to our example. At the root, it checks if x is less than 5. If x is greater than or equal to 5, we go right and immediately predict the square class. If x is less than 5, we go left and check if y is less than 5. If y is less than 5, we predict a mixed class. If y is greater than or equal to 5, we predict the circle class. And this is how decision trees recursively partition the data based on feature values, creating a series of decision rules that lead to predictions. A decision tree consists of 4 key components that work together to create a powerful predictive model. Let's start with the root node. This is the starting point of any decision tree, representing the first feature used to split our data. Next, we have internal nodes. These are decision points that split the data further based on additional features. Branches connect our nodes and represent possible decisions or outcomes from each decision point. Finally, we have leaf nodes. These are terminal nodes that provide the final predictions or classifications from our model. Together, these components form a complete decision tree structure. The model makes predictions by traversing from the root node through internal nodes, along branches until reaching a leaf node. For example, if we have a customer under 30 with a high income, the model would predict they will buy the product. Decision trees make predictions by following a series of rules, but how do they decide which rules to create? Trees use mathematical criteria to determine the best feature to split on at each node. The 3 most common splitting criteria are Gini impurity, entropy, and information gain. Each splitting criterion helps identify which feature provides the most information for classification. The goal is to find the split that best separates our data into pure classes. Initially, our data is often mixed. A good split will separate the data into subgroups that are more pure than the original data. After a good split, each resulting node should contain data that is more homogeneous. Our splitting criteria help us mathematically determine which split achieves this best. Gini impurity measures the probability of incorrectly classifying an element if it were randomly labeled according to the class distribution in the node. Let's calculate Gini impurity for a node with 20 samples, 15 from class 1 and 5 from class 2. The probability for class 1 is 0.75 and for class 2 is 0.25. Plugging these into our formula, Gini equals 1 minus the sum of squared probabilities, which gives us 0.375. Entropy measures the impurity or uncertainty in a node. It reaches its maximum when all classes are equally likely, and is 0 when all samples belong to one class. Information gain measures the reduction in entropy achieved by a split. It's calculated as the entropy of the parent node minus the weighted average of entropies of its children nodes. Here's a visual example of information gain. Our parent node has an equal mix of both classes, giving an entropy of 1.0. After splitting, each child node has a more pure distribution with 80% of one class and 20% of the other, resulting in lower entropy values of 0.72. The information gained from this split is 0.28, calculated as the parent entropy minus the weighted average of the children's entropies. Let's compare Gini impurity and entropy as splitting criteria. Both are valid measures of node impurity, but they have subtle differences. Despite these differences, both criteria often produce similar trees. Gini impurity is computationally more efficient since it doesn't require logarithm calculations. When dealing with multiple classes, entropy may sometimes perform better. Despite their advantages, single decision trees have significant limitations that affect their performance. Let's explore 4 major limitations that make individual decision trees less effective for complex problems. The first major limitation is overfitting. Single decision trees tend to create overly complex models that memorize the training data. Compare a generalized tree to an overfit tree, which creates many specific rules that match training examples perfectly, but fail on new data. The second limitation is instability. Decision trees are extremely sensitive to small changes in the training data. Even minor modifications to the dataset can result in completely different tree structures and decision rules. A third limitation is that decision trees struggle with imbalanced datasets, where one class significantly outnumbers others. In these scenarios, trees often create rules that favor the majority class while ignoring the minority class, even when minority examples represent important patterns. The fourth limitation is the bias toward features with more levels or unique values. Decision trees naturally favor features with many unique values, like postal codes or ID numbers, over binary features that might actually be more predictive. These fundamental limitations of single decision trees motivate the need for more advanced techniques, particularly ensemble methods. Ensemble methods combine multiple trees to overcome these weaknesses, creating more robust and accurate models.